value that should be replaced, that should replace the variables for that binding. And then the body is instantiated in a bigger term. But so what is this this value that we should pass in? So the information we have got available at this point is the context of the lambda gamma, so the output context. And well, we want to have something of the karyotype, so something of type x that we can pass in. So we have to come up with a function, make x y. So basically what we like to do, we have got two contexts available. We've got the context of the lambda, our gamma, and we also later on have a context at the reference side of the variable, which is supposed to be a super context. So we never remove any variables from the context. So what we could actually do, or what we would like to do, is define a predicate that encodes the supercontext relationship, and then given a proof that actually the inner context is gamma extended with one new variable should produce a proof that that very variable is in the context. So well, these definitions are possible. It's just a bit of arithmetic, but unfortunately we can't get such a proof. So as I mentioned earlier, one of the benefits of forwards is that the context is handled explicitly, and the representation I showed you doesn't give you this information. So this proof is not available. What we can do, circumvent the type checker. Yes. Okay. And actually decide that predicate in the positive case we get the proof, in the negative case we're partial undefined. Okay. So in the paper you find a generalization of the universe. I cover recursive and sequential scoping is covered. So for the explicitity, but it's actually very technical. Also a representation that is able to encode world typing. So we've got families at the moment, but that only covers finite families, and the simply typed languages are basically infinite families. You also have got the complete technical development of the generic conversion for the universe that covers recursive and is sequential scoping, but the details are not very important here if you like the paper. Okay, so let me conclude. I've shown you a generic approach to handle all the boilerplate of syntax operations, and actually this one's very expressive in a couple of senses. First of all, it covers realistic languages that have both sophisticated binding forms. It also covers representations that are well scoped or even well typed. And moreover, the universe, so the universe codes, they are generic in the sense that you can interpret them using different approaches to syntax. So I've shown you a De Broglie and forwards, but actually also a nominal approach, and so on. All of these are possible. Bit of future work. So when I started this, the goal was actually to provide a Haskell implementation for all of this. There are a couple of things which don't work out with forwards because of limitations of the Haskell type system. So one specific one is that using type families we can't really compute that well with polymorphic types. But for example, the syntax representations and the conversion are, it's possible to define them, so that's what ADKey has done. However, providing a generic implementation is difficult. But we can give an interpretation using the drawn terms, so this is totally possible. Even, although not for simplified representations. Also, it would be interesting to look at other generic functionality. So I've also covered, even more today, things like substitutions. But we have got the recursive positions available, so we could also look at generic zippers for syntax. Another thing is, well, we have substitutions or definitions of substitutions for syntax representations. What we also like to do is to have proofs available so communication proofs for the substitutions which we can use in reasoning for mechanized meta theory. So I've extended multi-rec. The question is what other approaches to data type generic programming can be extended with variable binding, and where is the trade-off between which generic functions I can define and which representation they cover. Yeah, I've only covered the broad terms and for us, but on also with others. So, thanks for your attention.
Okay, thank you, Stephen. The discussant for this session will be Stephanie Weiner. And she'll ask questions.
Okay. Well, let me just start off with a little preamble. First of all, thanking the chairs for inviting me to be the discussant for this paper. I very much enjoyed reading the paper. It's a technical paper, yes, but there's a lot of good stuff in there. Right? I really enjoyed sort of like the motivation disciplines in real time. So what I wanted to talk a little bit about why I enjoyed reading the paper and what I really like about this paper. So first of all, it's on a good topic. I really like it. I really think that dealing with variable binding is just this really good application of generic programming, and I wish we did it more, right? Not just in writing tools to help us write compilers, but also in writing tools to help us do formal meta theory. And that brings me to another point: is I liked how this paper was agnostic about what you wanted to use it for. Right? You're doing it in AGDA, which is both a theorem proof assistant and a programming language, and you didn't really say what you were thinking about. And so I got to imagine both. Right? Another thing I really liked about the paper was the section on pattern binding, right? Because that's something that I feel like is something that's often ignored by people who think about variable binding, right? And it's really important for people who use tools to help them with variable binding, like who write compilers or who do formal meta theory, having good support for pattern binding. And your section, it was kind of near the end of the paper, so it took a while to get there, but the sections where you talk about doing pattern binding with your ground indices and doing pattern binding with your higher order abstract syntax, those were some really nice sections of the paper. Maybe it's not necessarily all that new, but it's really good to have that written down somewhere so that we can see just how to do that, right? And I really also liked how concrete the paper was. It was a literate Haskell script, right? And so I felt like I really could play along with it. In fact, on my way here, while I was traveling here, I started part of your future work of putting it into Haskell. I just started playing around the first couple of pages, typing into Haskell just so that I could figure out what was going on, and it worked really well. So lots of fun. Let me make sure I said everything. Oh, one more point that I wanted to make about the paper is that your application, you use generic programming. There's more. You use generic programming for two different versions of how to two different representations And I wanted to point out that that's actually a really important thing to do, because whenever we represent variables in a language, we have this issue of adequacy. Are we adequately encoding the lambda calculus? And how do we know that? We don't really, you can't really write a proof or prove in your theorem prover that this is an adequate representation of lambda calculus. Because the lambda calculus, your theorem prover doesn't know what the lambda calculus is until you tell it. And so one way that you can gain confidence in your representation is to actually do several representations and prove that they're equal to each other. And the core of that proof is this translation function from the nested round indices and the higher order abstract syntax, right? And so you generically create those translations. Did you actually do any proofs to prove that you actually get an isomorphism out?
No.
No.
Yes.
Yeah.
So it would be very, well, API has done it for this representation, or just for the untitled chapters, but well, this establishes this link much more generally. And yeah, you would want to elaborate on that.
Yeah. And then one more thing, which is this paper is also an example of generic programming with index data types. Right? So we took a lot of data type generic programming in Haskell, but not so much with index data types like the GADT. But it's here. And if you're going to do generic proof development, you're going to really have to be able to do that, because you're going to represent your proofs with an index data structure. And writing a generic substitution right? Well, this is the way it happens. Okay, so questions. Actually, you answered most of my questions. Right, so I was going to ask you about doing it in Haskell, right? And I really think that, you know, exercise at home with the class, translate this paper into Haskell, right? Right, and I didn't get as far as the higher order abstract syntax, so I didn't see any of the issues that you were saying that you had in Haskell with the higher order. You said it was with type families?
Yeah.
Yeah.
So why would you want to do it in Haskell?
So you can play with new features of Haskell, like data type conversion and kind polymorphism.
The excellent one, you're from.
I didn't run them. It's actually a good comparison of just how handling type Haskell is. And I don't want to give, at least for, how far did I get? At least for the first 3 pages, after the pretty rough. I also wanted to ask you, like, so I said you were agnostic about whether you were doing it for implementing something or doing it for proving something. Did you use this code in either a proof or
yeah, so, well, in the Atlas standard library, there's actually data definitive substitutions, which, well, defines substitutions for terms using fin. But it also comes with a library of proofs. So what I did is extend this library to care for more sorts. So that was just throwing in a couple of universal quantifications. And I also proved that so this library actually only needs one traversal function and one relation about the traversal function. So I can instantiate the traversal function. Unfortunately, I cannot prove the relation for the richest. What did I? No, I didn't. For the richest universe. So for the universe using recursive and sequential scoping. So once I restrict myself to just binding of a single variable, I can essentially get that relation and get the complete library for my representation. But unfortunately, it didn't work out for. So you would think it's just induction over the number of variables, but there are so many expressions, type expressions, which don't normalize to the same thing. So the type check, I can't see that they are the same, even though I know it. You have to resort to a lot of typecasting. That gets very nasty. So.
But another motivation was very practical. We wanted to use embedded languages in one of the tools we were building.
So this is
variables.
so this is stressed out.
We
much more in the paper than here, so I didn't even mention it. So, well, we have, well, what we want for domain-specific languages is to use the same features as for our normal languages, and so there are multiple benefits of embedding them. But we also want to have the representation types that we want to give a domain-specific type system and ensure that all the terms respect that typing. So, yeah. So, well, this has been done before, and so there are multiple examples of showing this. Still, we have to give an implementation of the DSL ourselves and generic operations for that. So, which have these, which meet these requirements of being expressive and being well typed. So, having a literature generic approach with colors is helpful in these other developments.
Because now we haven't used it yet. So I was really wanting this Haskell implementation, which we could use for our own tools.
Yeah, so GSC 7.6 was just released in the fix of the time promotion. So
who knows, maybe it's possible.
So this is also one thing, a program I ran into earlier, that I need to have lots of food terms to pass around. So I need well-formed-ness of context, well-formed-ness of context membership, and so on. So even though we don't have kind promotion for GABTs,
Another motivation for it.
yeah, it might get us further, or might get me further than the last time.
Okay, so I'm going to wrap up, but open for more questions. Or do we have time?
We have time for one question, so does anyone have any?
Yeah, well, I couldn't quite follow the talk, perhaps because I'm not that familiar with generic Haskell, and I should be. So sorry if you answered this question, and I didn't just I couldn't follow. You seem to want to have code reuse. As far as I can understand from your presentation, in the syntax level.
I want to have code reuse for syntax representations.
For the syntax
for representations of object languages in MetaPrograms. Yes.
And does that also enter semantics, or does it stop at the syntax level?
That basically stops at the syntax level. I mean, if you look at the lambda calculus and the semantics, so the evaluation of beta reduction is linked to substitution. And substitution is a pure syntactic operation.
Okay, so I seem to understand that you're telling me that it stops at the syntax level.
Yeah.
Right. Now then I didn't quite get how you make a comparison with opt. So because opt doesn't stop at the syntax level, it goes a bit further.
Yeah, it goes. Well, I don't know the specifics of opt, but well, for doing method theory, it gives you also proof stuff. Yeah. So which specific operations or which features?
So for example, you can opt, you can prevent certain semantic mistakes because you can provide room for your language.
Yeah.
Derivation rules, and then if you for example make certain kinds of typos in the instruction of those rules, then opt will error.
Okay.
And that not necessarily is related to syntax. It might be that it goes further. I couldn't quite get how this is related to it.
Well, I think you meant to be the relation between the syntax representation there and the syntax representation used for you, right? I don't think you're comparing the full functionality of opt.
Okay.
No, but I also don't understand why you're saying you're stopping at syntax. Of course, isn't the ultimate goal is to have a generic syntax representation so that you can write all sorts of generic functions over it. And that will automatically go into the semantic realm of the website.
And the examples of the type syntax kind of resemble some of the rules that you get in OT, right? In OT, you have like those two separations. You have grammar, which is not indexed at all, which is a plain data type, and then you have the rules that are like typing rules. But when he had the strongly typed syntax with lambda calculus, where you can only form well-typed lambda calculus terms, that's capturing some of the constraints that the OT rules give you.
Okay.
It's not as convenient as OT a little bit, because OT has a lot of convenience factors. But there are some ways of using index data types to capture some of the constraints that type rules.
Right. And then ops. So when it comes to code reuse and semantics development, ops takes the extreme end, which is code reuse in copy-pasting the root. Whereas people like Peter Moss's, they think of executability as the parameter, as the important, the significant parameter for code reuse. Where in this spectrum are you?
Sorry,
Actually, I think we're
Right, we can
running
take,
over.
yeah, we can take it offline, yeah.
Okay. So we have a break until 4.